Chapter 6, Number 10. A person places a cup of coffee on the roof of his car while he dashes back into the house for a forgotten item. When he returns to the car, he hops in and takes off with the coffee cup still on the roof. If the coefficient of static friction between the coffee cup and the roof is 0.24, what is the maximum acceleration the car can have without causing the cup to slide? Ignore the effects of air resistance. And what is the smallest amount of distance in which the car can accelerate from rest to 15 meters per second and still keep the coffee cup on the roof? This is a little strange because what we have to look at here is friction does different than we're used to. So we have this, and here is our cup, and the car accelerates, and we need the acceleration of the cup to be the same. If the cup accelerates less than the car, then it will, from the point of view of the driver, slide backward and eventually fall off the roof of the car. So if we look at just the cup, its free body diagram is going to look like this. There's going to be its weight pulling it downward, and there's going to be a normal force from the roof holding it in place, and there's going to be a frictional force, and now we have to be a little careful. The car moves to the right, so friction wants the cup to not slide along the roof, which means it must have the same velocity as the roof, which means friction actually pushes this thing forward. We usually think of friction as retarding motion. Here it actually causes the cup to move forward, keeping them together with the roof. All right, after that, it's not too bad, because what we can do is we can start saying, well, the sum of our forces in the x direction is just the force of friction, and the sum of the forces in the y direction is the normal force minus the weight. That's from, of course, the free body diagrams. From Newton's second law, we have the sum of the forces in the x direction is the mass times the acceleration, and the sum of the forces in the y direction is the mass times 0, or 0. So putting those two things together, we have that FF equals ma, and Fn minus Fg equals 0. This tells us that Fn equals Fg, which is always the mass times g. And we know that the frictional force is, since this is static, it's less than or equal to mu Fn, mu static Fn, because we want the cup to not slide along the roof. All right, so we have then, we can put this together and say that ma is less than or equal to mu s times mg, where what I've done here, of course, is taken this and put it here, and I've taken this and put it here. And then we can just cancel out the m's, and we get that a has to be less than or equal to mu s times g. So mu s times g is 0.24 times 9.81 meters per second squared. So the acceleration needs to be less than or equal to 2.3544 meters per second square. And then we know that we have only two sig figs, so it's really saying that a must be less than or equal to 2.4 meters per second square. And that's part A. Part B says, what's the smallest amount of distance over which, smallest amount of time in which the person can accelerate from rest to 15 meters per second and still keep the cup on the roof? So this is actually now a kinematics problem, not a dynamics problem, since we now have the acceleration. And we're just going to use that at any time, the velocity is the initial velocity plus the acceleration times the time. So our final velocity is going to be just the acceleration times the time it takes us to get there. The time, therefore, is going to be the velocity, final velocity desired over the acceleration. To minimize the time, we maximize a, so we use the a we just found. So we're going to say 15 meters per second over the 2.4 meters per second squared, and we're going to find 6.25 seconds, which really rounds to 6.3 seconds. So if they get to 15 meters per second any quicker than 6.3 seconds, the coffee cup will slide at least a little bit.